Welcome everyone to this academic lecture on THMC coupling for CO₂ storage and underground hydrogen storage. Today we will connect four important physical and chemical processes: thermal, hydraulic, mechanical, and chemical behavior. These four letters may look simple, but together they control injectivity, containment, plume migration, fault stability, mineral trapping, hydrogen deliverability, and long-term safety. In this video, I will explain the concepts from pore-scale to reservoir scale, then show how they support modern storage design and digital twin monitoring. Let us start by asking one key question. What really happens underground after we inject CO₂ or hydrogen? This topic is important because subsurface storage is becoming a central technology for both climate mitigation and energy security. CO₂ storage helps us reduce industrial emissions by keeping carbon dioxide underground for hundreds to thousands of years. Hydrogen storage, on the other hand, helps balance renewable energy by storing large amounts of energy seasonally. However, both technologies depend on the same deep subsurface physics. If we do not understand pressure, temperature, stress, chemistry, and their feedbacks, we cannot design safe projects. So in this lecture, THMC becomes the scientific language for reliable storage. Here is the roadmap for the video. We begin with the basic meaning of thermal, hydraulic, mechanical, and chemical coupling. Then we apply the framework to CO₂ storage, where the main goal is containment and permanence. After that, we move to underground hydrogen storage, where the main goal is repeated injection and withdrawal with high deliverability and high gas purity. Finally, we discuss modeling, monitoring, uncertainty, machine learning, and digital twins. The story moves from pores to cores to reservoirs to operational decisions. This structure will help students and professionals see the complete picture. CO₂ and hydrogen may use similar geological formations, but they ask very different engineering questions. For CO₂ storage, the key question is, will the injected CO₂ stay underground safely and permanently? We focus on trapping, pressure management, caprock integrity, and leakage prevention. For hydrogen storage, the key question is, can we inject and withdraw hydrogen efficiently again and again? We focus on working gas, cushion gas, purity, cyclic pressure, and deliverability. This contrast is very powerful. CO₂ storage is mainly about permanence, while hydrogen storage is mainly about flexibility and energy supply. THMC stands for thermal, hydraulic, mechanical, and chemical processes. Thermal means temperature and heat transfer. Hydraulic means pressure, saturation, multi-phase flow, capillary pressure, and relative permeability. Mechanical means stress, strain, deformation, fault stability, and fracture behavior. Chemical means dissolution, precipitation, mineral reactions, microbial reactions, and gas-rock brine interaction. The most important point is that these processes do not act independently. Temperature changes viscosity and reaction rates. Pressure changes effective stress. Chemical reactions change porosity and permeability. This is why a coupled THMC view is essential for storage engineering. This slide can be used as the first animation in the video. Imagine that injection starts at the well. First, a pressure pulse moves outward. Then the gas plume begins to migrate through connected pore space. The saturation distribution changes, and this modifies relative permeability and capillary forces. At the same time, pore pressure changes the effective stress in the rock. If the fluid is reactive, chemical reactions begin along the flow path. So a single engineering action, injection, creates a chain reaction across the reservoir. This is the core idea of THMC coupling. In part 1, we build the foundation. Before we talk about CO₂ storage or hydrogen storage separately, we need a common vocabulary. What is a thermal front? What is pressure buildup? How does pore pressure influence stress? Why does chemistry affect porosity and permeability? These questions are not only theoretical. They determine whether an injection plan is safe, whether a storage site is efficient, and whether monitoring data can be interpreted correctly. So let us begin with each component of THMC and then connect them into one integrated system. The thermal process is more than just temperature. In the subsurface, temperature controls fluid density, viscosity, solubility, reaction rate, and even mechanical stress. The initial temperature is often governed by the geothermal gradient. When we inject CO₂ or hydrogen, the injected fluid may be colder or warmer than the reservoir. This creates a thermal front. In gas systems, expansion and pressure changes can also create cooling effects. These thermal changes may look small, but near the wellbore they can strongly affect injectivity, reaction kinetics, and stress concentration. Now let us connect temperature to mechanics. If the reservoir rock cools, the rock tends to contract. But the rock is not free to contract because it is surrounded by other formations. This constraint produces thermal stress. Near an injection well, cooling may generate tensile stress and may influence fracture risk or wellbore integrity. In CO₂ storage, this is important for caprock safety and fault stability. In hydrogen storage, repeated thermal and pressure cycles may also influence fatigue-like mechanical behavior. Therefore, thermal stress should not be ignored in rigorous storage analysis. Temperature also influences hydraulic behavior. Fluid viscosity, density, solubility, and compressibility all depend on temperature. If viscosity changes, mobility changes. If density changes, buoyancy changes. If solubility changes, dissolution trapping or gas loss changes. This means a thermal front can become a mobility front. In CO₂ storage, temperature can affect CO₂ brine phase behavior and dissolution. In hydrogen storage, temperature affects gas density and deliverability. So even when our main interest is flow, temperature can still control how fast and where the gas moves. The hydraulic process is the engine of storage. It describes how pressure and saturation evolve through time. Pressure controls injectivity, brine displacement, geomechanical loading, and communication with boundaries or faults. Saturation tells us where the gas is present and how much of the pore volume is occupied by gas and brine. In CO₂ storage, saturation maps help us understand plume migration and trapping. In hydrogen storage, saturation controls the working gas and residual gas after withdrawal. Without reliable hydraulic modeling, we cannot estimate storage capacity, operational pressure, or recovery efficiency. At the pore scale, capillary pressure and relative permeability control large-scale plume behavior. Capillary pressure determines how much pressure is needed for gas to enter smaller pores or caprock pores. Relative permeability determines how easily each phase flows when gas and brine coexist. Hysteresis is especially important because drainage and imbibition do not follow the same path. For CO₂ storage, hysteresis helps explain residual trapping. For hydrogen storage, hysteresis affects how much hydrogen remains trapped after withdrawal and how much can be recovered in each cycle. When we inject gas, pore pressure increases. This pressure buildup is controlled by injection rate, permeability, boundary conditions, fluid mobility, rock and fluid compressibility, and brine displacement. A high permeability reservoir may distribute pressure more efficiently, while a low permeability or closed system may build pressure rapidly. The pressure plume can be much larger than the visible gas plume. This matters because faults or old wells may respond to pressure even when the gas itself never reaches them. Therefore, pressure management is one of the most important design tasks in storage projects. The mechanical process begins with the concept of effective stress. Total stress is carried by both the rock skeleton and the pore fluid. When pore pressure increases, the effective stress carried by the rock skeleton decreases. This can change compaction, dilation, fracture tendency, and fault stability. In simple terms, increasing pore pressure can make the rock and faults mechanically weaker. This is why flow simulation alone is not enough for safe storage design. We must connect pressure evolution to mechanical response, especially near faults, caprock, and wellbores. Fault stability is one of the clearest examples of hydraulic mechanical coupling. A fault can slip when shear stress becomes large relative to the effective normal stress and frictional resistance. Injection increases pore pressure, and increased pore pressure reduces effective normal stress. As a result, a fault may become less stable even if CO₂ or hydrogen does not directly contact the fault. This is why the pressure footprint is often more important than the gas plume for induced seismicity assessment. In storage engineering, we need to know not only where the gas goes, but where pressure communicates. Mechanical deformation can appear as uplift, subsidence, compaction, dilation, or localized strain. Pressure increase may expand the reservoir and create surface uplift. Pressure relief through brine production may reduce overpressure, but excessive withdrawal can increase compaction and subsidence. Deformation is not always negative. It can also provide useful monitoring signals. For example, surface displacement measured by satellite or ground instruments can help infer pressure distribution underground. In THMC storage analysis, deformation is both a risk indicator and a valuable source of information. CO₂ storage has a strong chemical component. When CO₂ dissolves in brine, it forms carbonic acid and lowers pH. This acidic brine can dissolve minerals, release ions, and change porosity and permeability. Over longer times, secondary minerals may precipitate and permanently trap carbon as solid minerals. This mineral trapping is one of the most secure forms of CO₂ storage, but it is usually slower than structural or residual trapping. The key message is that chemistry can modify the reservoir itself. Flow changes chemistry, and chemistry changes flow. Hydrogen storage has different chemical challenges. Hydrogen is not simply an inert gas underground. It can interact with minerals, brine, wall materials, and microorganisms. Under certain conditions, microbes may consume hydrogen and produce methane or hydrogen sulfide. These reactions can reduce hydrogen recovery and affect gas purity. Mineral reactions may change pH, ionic composition, and possibly permeability. In addition, hydrogen can influence material integrity in wells and surface facilities. Therefore, the chemical part of THMC and hydrogen storage is strongly connected to purity, loss, safety, and economics. This coupling matrix summarizes the main idea. Every process can influence every other process. Thermal changes affect hydraulic properties such as viscosity and density. Hydraulic changes affect mechanical stability through effective stress. Mechanical deformation changes porosity and permeability, which then feeds back to flow. Chemical reactions can dissolve or precipitate minerals, altering pore structure and transport pathways. In real reservoirs, these feedbacks may occur at different time scales. Some happen near the well within hours or days. Others happen over years or decades. A complete model must recognize these different couplings. The academic backbone of THMC modeling is a set of conservation laws and constitutive relations. We need mass balance for each fluid component, energy balance for heat transfer, and momentum balance for mechanical deformation. We also need constitutive models for capillary pressure, relative permeability, phase behavior, geochemistry, rock elasticity, plasticity, and fault friction. A THMC simulator is therefore not one equation. It is a system of strongly connected equations. The challenge is to solve them accurately enough for science, but fast enough for engineering decisions. Now we apply this framework to geological CO₂ storage. The purpose of CO₂ storage is to inject carbon dioxide into a deep geological formation and keep it there safely for the long term. In this part, we will discuss storage systems, trapping mechanisms, plume evolution, pressure management, salinity effects, geomechanics, chemistry, leakage pathways, monitoring, and animation storytelling. The main message is that CO₂ storage is not only about putting CO₂ underground. It is about managing the complete reservoir caprock fault well system through time. A CO₂ storage project is an engineered geological system. The reservoir must have enough capacity and injectivity. The caprock must have enough sealing capacity. Faults and legacy wells must be evaluated as potential leakage pathways. The injection well must be designed to operate safely under pressure, temperature, and corrosion conditions. Monitoring must be planned before injection begins. In a good storage site, geology and engineering work together. The reservoir accepts CO₂, the caprock contains it, and monitoring provides evidence that the system behaves as expected. CO₂ is trapped by several mechanisms. Structural trapping occurs when buoyant CO₂ accumulates beneath a sealing caprock. Residual trapping occurs when CO₂ becomes disconnected as small ganglia in pore spaces. Solubility trapping occurs when CO₂ dissolves into brine. Mineral trapping occurs when dissolved carbon reacts with minerals and forms stable solid phases. These mechanisms operate at different time scales. Early storage may rely more on structural and residual trapping. Over longer time, solubility, and mineral trapping can increase security. The best projects use geology and operations to promote multiple trapping mechanisms. CO₂ plume evolution is controlled by injection, buoyancy, permeability structure, capillary pressure, and trapping. Near the well, injection pressure dominates. As CO₂ moves away, buoyancy may cause upward migration, especially because CO₂ is less dense than brine. Heterogeneity can create preferential pathways, barriers, or fingering. Residual trapping immobilizes part of the plume during migration, and dissolution gradually transfers CO₂ into the brine phase. When you animate this slide, show the plume growing first, then spreading laterally, then becoming less mobile through trapping and dissolution. Pressure management is central to safe CO₂ storage. The free-phase CO₂ plume shows where CO₂ saturation is high, but the pressure footprint may extend much farther. This pressure footprint can influence faults, nearby wells, caprock integrity, and even neighboring storage projects. Engineers can manage pressure by adjusting injection rate, selecting well locations, using multiple injectors, producing brine, or choosing formations with better hydraulic connectivity. A key teaching point is this: a project can have a small CO₂ plume, but still a large pressure footprint. Both must be evaluated. Salinity is often underestimated, but it can strongly influence CO₂ storage behavior. Brine salinity affects CO₂ solubility, brine density, brine viscosity, and overall pressure response. Higher salinity often reduces CO₂ solubility, meaning less CO₂ dissolves into brine. This can influence mobile CO₂ volume, pressure buildup, and trapping efficiency. Accurate PVT modeling is therefore essential, especially in high salinity aquifers or depleted reservoirs. In academic research, salinity is also a strong example of why fluid properties should be linked to THMC behavior, not treated as fixed constants. In CO₂ storage, fault reactivation risk comes from the link between pore pressure and effective stress. Injection raises pore pressure. Higher pore pressure reduces effective normal stress on faults. If the fault is already close to failure, this reduction may trigger microseismicity or slip. Importantly, the risk can occur even without direct CO₂ contact, because pressure can communicate through the brine phase. This is why geomechanical modeling should be integrated with flow modeling. A safe project must evaluate not only storage capacity, but also the stress state of the surrounding geological system. The chemical story of CO₂ storage starts with dissolution. CO₂ dissolves into brine, forms carbonic acid, and lowers pH. This acidic fluid can dissolve minerals and release ions such as calcium, magnesium, or iron, depending on the rock type. Later, new minerals may precipitate and store carbon in a stable solid form. This process can improve long-term security, but it may also alter permeability near reaction fronts. In sandstone, carbonate, and basaltic systems, the details can be very different. Therefore, geochemistry must be site-specific. Leakage risk is often localized at discontinuities. Caprock fractures, faults, abandoned wells, and high permeability streaks can become critical pathways. THMC processes can either increase or decrease this risk. Pressure can open fractures. Thermal stress can change near well integrity. Chemical reactions can dissolve cement or minerals, but they can also precipitate sealing phases. Mechanical slip can change fault permeability. A robust storage project identifies these weak links early, models how they respond to injection, and designs monitoring to detect unexpected behavior before it becomes a serious problem. Monitoring is how we convert hidden subsurface processes into evidence. Seismic monitoring can track plume geometry and saturation change. Pressure monitoring can reveal hydraulic connectivity, boundary effects, and pressure buildup. Geochemical monitoring can detect dissolved CO₂, pH changes, tracers, or leakage indicators. Deformation monitoring can show uplift or subsidence related to pressure changes. The best monitoring plans are designed around risk drivers. We do not monitor everything randomly. We monitor the signals that tell us whether the THMC system is behaving safely. We can consider CO₂ storage as a 6-frame story. Frame 1, site screening, where geology is evaluated. Frame 2, injection begins, and pressure starts to rise. Frame 3. The CO2 plume grows and migrates. Frame 4. The pressure footprint spreads beyond the plume. Frame 5. Monitoring updates the model using seismic, pressure, geochemical, and deformation data. Frame 6. Operation is adjusted to manage risk. This storyboard helps viewers understand cause and effect. It also makes CO2 storage feel like an active engineering system, not a static underground tank. Now we move to underground hydrogen storage. Hydrogen storage is different from CO2 storage because the target is not permanent disposal. The target is repeated cycling. Inject hydrogen when renewable energy is abundant and withdraw it when energy demand is high. This repeated operation creates dynamic pressure, saturation, stress, and possible geochemical or microbial changes. The keywords in this part are deliverability, gas purity, cushion gas, working gas, capillary sealing, hysteresis, cyclic geomechanics, and operational flexibility. Hydrogen storage is a very exciting frontier for subsurface engineering. Underground hydrogen storage converts geological pore volume into large-scale energy storage. During periods of surplus renewable electricity, hydrogen can be produced and injected underground. During periods of high demand, it can be withdrawn and used for power, industry, or transport. The storage system may include an injection withdrawal well, a reservoir or cavern, surface compression facilities, monitoring systems, and gas treatment units. The engineering challenge is to maintain pressure, purity, containment, and deliverability over many cycles. This makes UHS a true THMC and energy systems problem. Hydrogen can be stored in several geological systems. Salt caverns usually provide high deliverability and strong sealing, but they are limited by suitable salt geology and construction cost. Depleted gas reservoirs have known traps and existing data, but may contain residual methane and complex reservoir heterogeneity. Saline aquifers may offer large capacity, but they are often less characterized and may need more uncertainty analysis. Each option solves a different energy storage problem. Salt caverns are strong for short-term balancing, while porous reservoirs may become important for seasonal storage. Hydrogen storage is fundamentally cyclic. One cycle includes injection, shut-in, withdrawal, and re-injection. During injection, pressure increases and hydrogen saturation grows. During withdrawal, pressure decreases and part of the gas is recovered, while some remains as residual or cushion gas. Repeating this process many times creates hysteresis in relative permeability and capillary pressure. It also creates repeated stress paths in the rock. Therefore, the operation itself becomes the physics. To model UHS correctly, we must simulate not only one injection event, but many cycles. Hydrogen has properties that make it both attractive and challenging. It has low viscosity, so it can move easily and may provide strong deliverability. But high mobility may also increase fingering, gravity override, or leakage risk in some systems. Hydrogen has low density, so buoyancy can be important. Its high diffusivity and small molecular size raise questions about sealing, materials, and loss mechanisms. Hydrogen may also participate in microbial or geochemical reactions. In short, hydrogen is not simply a smaller version of natural gas. It needs its own storage science. At the pore scale, hydrogen interacts with brine and rock surfaces. What ability controls whether hydrogen occupies larger pores, how easily it enters caprock pores, and how much residual gas remains after withdrawal? Capillary pressure controls entry pressure and trapping. Relative permeability controls deliverability. Brine chemistry and mineral surfaces can influence interfacial tension, contact angle, and reactions. These pore-scale interactions scale up to reservoir-scale performance. For YouTube teaching, this is a powerful point. Tiny pore-scale forces can control large-scale energy storage efficiency. At the pore scale, hydrogen interacts with brine and rock surfaces. What ability controls whether hydrogen occupies larger pores, how easily it enters caprock pores, and how much residual gas remains after withdrawal? Capillary pressure controls entry pressure and trapping. Relative permeability controls deliverability. Brine chemistry and mineral surfaces can influence interfacial tension, contact angle, and reactions. These pore-scale interactions scale up to reservoir-scale performance. Microbiology is one of the most unique challenges in underground hydrogen storage. Some microorganisms can use hydrogen as an energy source. For example, methanogens may convert hydrogen and carbon dioxide into methane. Sulfate-reducing bacteria may contribute to hydrogen sulfide generation under favorable conditions. These processes can reduce hydrogen purity, consume stored hydrogen, and create corrosion or safety concerns. Microbial activity depends on temperature, salinity, nutrients, pH, minerals, and residence time. This is why H2 storage must consider not only physics, but also geochemistry and microbiology. In hydrogen storage, not all injected gas is meant to be recovered immediately. Cushion gas is the gas volume that remains underground to maintain reservoir pressure and deliverability. Working gas is the gas volume that is repeatedly injected and withdrawn. The economics of UHS depend strongly on maximizing working gas while maintaining enough cushion pressure. Cushion gas may be hydrogen, nitrogen, methane, or a mixture, depending on project design. THMC modeling helps determine how much gas is needed, how much can be recovered, and how pressure evolves through cycles. Capillary sealing is critical for hydrogen containment. For hydrogen to enter caprock pores, it must overcome capillary entry pressure. This entry pressure depends on interfacial tension, pore throat size, contact angle, and brine chemistry. If wettability changes, sealing capacity can change. This is why laboratory measurements and site-specific capillary models are important. For CO₂ storage, caprock sealing is linked to permanence. For H2 storage, sealing is linked not only to safety, but also to loss prevention and gas purity. A good caprock protects both the environment and the project economics. Hydrogen storage is not a single injection event. It is repeated loading and unloading of the reservoir. During injection, pressure increases and effective stress decreases. During withdrawal, pressure decreases and effective stress increases again. Over many cycles, this changing stress path may influence compaction, dilation, fault stability, or well integrity. The key question is whether the storage formation remains elastic, stable, and sealed over long-term operation. Cyclic geomechanics therefore becomes a major difference between CO₂ storage and hydrogen storage. Deliverability is the bridge between geology and the energy system. A reservoir may have large capacity, but if hydrogen cannot be withdrawn fast enough, it may not support energy demand. Deliverability depends on permeability, thickness, pressure support, relative permeability, while completion, skin, reservoir heterogeneity, and surface compression. It also depends on the cycling strategy. In THMC terms, deliverability is mainly hydraulic, but it is influenced by mechanical deformation, thermal effects, and chemical or microbial changes. For UHS, deliverability is not a detail. It is the main performance indicator. In Part 4, we discuss how to model THMC systems. Conceptual understanding is important, but engineering decisions require quantitative prediction. We need to estimate pressure, saturation, stress, deformation, reaction progress, leakage risk, and deliverability under uncertain geological conditions. This requires simulators, laboratory data, monitoring data, uncertainty quantification, and increasingly machine learning. The goal is not only to produce colorful maps. The goal is to support safer decisions: where to inject, how fast to inject, when to withdraw, and how to update operations when new data arrive. A strong THMC workflow connects multiple scales. At the pore scale, imaging and experiments help us understand wettability, capillarity, and reactions. At the core scale, laboratory tests provide relative permeability, capillary pressure, mechanical properties, and geochemical parameters. At the reservoir scale, simulation predicts plume movement, pressure buildup, stress change, and operational performance. At the basin or project scale, models support risk ranking and monitoring design. This multi-scale pathway is essential because we cannot measure everything at field scale directly. We must combine evidence across scales. A THMC model is only as good as its input data. We need static geological data such as structure, stratigraphy, faults, facies, porosity, and permeability. We need fluid properties such as PVT, salinity, viscosity, density, solubility, and interfacial tension. We need rock mechanical properties such as Young's modulus, Poisson's ratio, strength, friction coefficient, and in situ stress. We also need chemical and microbial parameters where reactions matter. Finally, we need operational data, injection rate, pressure limits, well geometry, and monitoring observations. Data integration is the foundation of credible prediction. There are different strategies for solving THMC models. Fully coupled simulation solves flow, heat, mechanics, and chemistry together, capturing strong feedbacks, but it can be computationally expensive. Sequential coupling solves one physics first and passes information to another, which is faster and more flexible, but may lose stability when feedbacks are strong. One-way coupling can be useful when feedback is weak, for example using pressure from flow simulation to drive geomechanics. The best strategy depends on the question. For screening, fast methods may be enough. For critical risk analysis, stronger coupling may be needed. A digital twin is a living model of the storage system. It combines simulation, monitoring data, uncertainty analysis, and decision support. Sensors provide pressure, seismic, geochemical, deformation, and operational data. The model is updated by history matching or data assimilation. Then it forecasts future behavior under different operational options. The final output is not just a map, it is a decision. Continue injection, reduce rate, add monitoring, produce brine, or change cycling strategy. Digital twins are powerful because they turn THMC modeling into adaptive storage management. Machine learning can accelerate THMC analysis. Full simulators are often too slow for thousands of uncertainty cases, real-time forecasting, or optimization. Surrogate models can learn relationships between geological inputs, operational controls, and outputs such as pressure, saturation, stress, or risk metrics. However, AI must remain physically credible. We should use conservation laws, physics-informed loss functions, uncertainty quantification, and validation against simulations and field data. In storage engineering, the goal is not AI replacing physics. The goal is AI accelerating physics-based decision-making. Uncertainty quantification is essential because the subsurface is never fully known. Geological uncertainty includes facies, faults, connectivity, and boundaries. Petrophysical uncertainty includes permeability, porosity, capillary pressure, and relative permeability. Geomechanical uncertainty includes stress state, friction, stiffness, and strength. Chemical uncertainty includes reaction rates and microbial activity. Instead of one deterministic prediction, we should generate ensembles and look at probability ranges. A robust storage design is one that remains safe and effective across many plausible geological scenarios, not only one best-case model. The monitoring-to-model loop is the heart of adaptive management. First, we observe the system using pressure, seismic, geochemical, and deformation data. Then we diagnose whether the observations match the model. If there is a mismatch, that is not a failure, it is information. We update the model, reduce uncertainty, and forecast again. Finally, we act by adjusting the operation or monitoring plan. This loop is especially important for long-term CO₂ containment and cyclic hydrogen storage. The system is dynamic, so our model must also be dynamic. Risk metrics translate complex THMC physics into operational decisions. For CO₂ storage, important metrics include pressure margin, fault stability, caprock integrity, plume containment, leakage probability, and trapping efficiency. For hydrogen storage, important metrics include deliverability, working gas recovery, purity loss, cushion gas requirement, capillary leakage risk, and cyclic mechanical stability. These metrics help engineers compare scenarios. Instead of saying one case has higher pressure, we can say whether it exceeds an operational limit or reduces a safety margin. Metrics make THMC results actionable. In the final part, we convert THMC understanding into design principles and teaching takeaways. By now, we have seen that CO₂ storage and hydrogen storage share similar subsurface physics, but have different objectives. CO₂ storage focuses on permanent containment and risk reduction. Hydrogen storage focuses on cyclic recovery and energy system flexibility. The same THMC framework helps us design both, but the performance indicators are different. This final section will summarize the comparison, design levers, operational playbook, monitoring strategy, research gaps, and key messages for students and professionals. This comparison slide is very important for you. CO₂ storage and hydrogen storage use the same THMC language, but the design priorities differ. CO₂ requires long-term containment, trapping, and pressure control over decades to millennia. H2 requires repeated cycling, high deliverability, and purity preservation over daily to seasonal timescales. CO₂ chemistry is often about dissolution and mineralization. H2 chemistry is often about microbial conversion, gas loss, and contamination. The lesson is simple. Do not copy CO₂ storage assumptions directly into H2 storage. Similar reservoirs can produce very different engineering problems. Engineers have several levers to shape THMC response. Rate control can limit pressure buildup. Well placement can avoid faults, improve sweep, and increase monitoring sensitivity. Pressure relief through brine production can reduce overpressure, but it must be designed carefully to avoid compaction or subsidence. Completion depth can influence plume shape and stress distribution. Cushion gas design can improve hydrogen deliverability. Monitoring design can detect early warning signals. The main idea is that safety is not only a property of the site, it is also a result of smart operation. A practical operational playbook has 6 steps. First, screen the site and identify weak links. Second, build a base geological, flow, mechanical, and chemical model. Third, run THMC ensembles to stress test uncertainty. Fourth, rank risks using clear metrics. Fifth, design monitoring around the most important risk drivers. Sixth, adapt operation as new data arrive. Before injection, the goal is to understand possible failure modes. During operation, the goal is to update forecasts. After operation, the goal is to demonstrate containment, stability, or recovery performance. Monitoring should be matched to the physics we need to observe. If the risk driver is pressure buildup, downhole pressure is essential. If the risk driver is plume migration, for seismic, logs, or tracers may be important. If the risk driver is fault stability, microseismicity, pressure, and deformation can be combined. If the risk driver is chemical change, fluid sampling and tracers are useful. For hydrogen, gas composition monitoring is especially important. A good monitoring plan is not just a list of tools. It is a logic chain from risk driver to signal to action. There are still many exciting research gaps. We need stronger field-scale THMC validation datasets that combine flow, stress, chemistry, and monitoring. For hydrogen storage, we need better hysteresis data under reservoir conditions and more experiments on hydrogen-brine-rock interactions. Microbial effects need to be integrated into reservoir scale prediction. Digital twins need faster, physics-constrained AI models. We also need better risk metrics that connect storage performance to energy system decisions. These gaps are not weaknesses. They are opportunities for future research and for educational content on this channel. Let us summarize the lecture in 4 key messages. First, storage is coupled. Pressure, temperature, stress, and chemistry evolve together. Second, CO₂ storage prioritizes permanence, so containment, trapping, pressure management, and long-term integrity dominate. Third, hydrogen storage prioritizes cycling, so deliverability, cushion gas, purity, and cyclic stability dominate. Fourth, digital twins connect models with monitoring data so storage can be managed adaptively. If viewers remember one sentence, it should be this: THMC coupling is the scientific bridge between subsurface physics and safe energy transition operations.